Hello friends, I welcome you in lecture number 37 on graph theory. In this lecture we will talk about binary search tree. Now we are familiar with trees and with binary tree also. We know that a binary tree is that tree in which every internal vertex has at most two children. If every internal vertex has at most two children in a tree, then that tree is called binary tree. And what is meaning of binary search tree, that we are going to understand in this lecture. So first we understand the definition of binary search tree. Suppose capital T is a binary tree, then T is called a binary search tree if each node or if every vertex denoted by capital N of tree capital T has the following property. If every node of binary tree has this property, then we will call that binary tree as binary search tree. So what is that property? The value of node n is greater than every value in the left subtree of n. Whatever subtree is to the left side of n, in that subtree the value of n is always greater than all these values which are in the left subtree of n, and the value of n is less than every value in the right subtree of n. For example, if we have on this side we have right subtree of n, then value of n is less than the value of every node in the right subtree of n. I have taken one example of binary search tree. Here we can understand that if I start with this root 38, then here we can see that the value of 38 is greater than every value in the left subtree of n. Left subtree means this part. If we consider this subgraph of this tree, then it is also a tree and it is called left subtree of this node 38. We can consider this type of perpendicular line, and the tree which is to the left side of this perpendicular line is left subtree, and the tree which is to the right side of this perpendicular line is considered as right subtree. So here we can see all these values 14, 8, 23, 18 all are less than 38. That is, the value in the left subtree of 38 is less than 38. All the values in the left subtree of 38 are less than 38. Similarly, all the values in the right subtree of 38 are greater than 38. And this must happen for every vertex. Suppose I am talking about 14, then the left subtree of 14 contains only one node which is 8, and we can see that this 8 is less than 14. And if we consider this part, then this is the right subtree of 14 and these two values are greater than 14. So in that sense you have to consider this definition. For example, if I consider 56, then it has left subtree with only one node and it is value is 45, and because it is to the left it is less than 45. So the tree which satisfies this property, or the binary tree which satisfies this property, is called a binary search tree. What is the property? The value of node is greater than every value in the left subtree of n, and the value of every node is less than every value in the right subtree of n. So they can ask you to write down the definition also. You can write in this way. Suppose we have some binary tree denoted by capital T, then T is called a binary search tree if every vertex capital N of T has the following property, and the property is the value of node n is greater than every value in the left subtree of n, and the value of node n is less than every value in the right subtree of n, and this must be true for every node. Now sometimes they can ask you to write down the or construct or design the binary search tree from the given data also. Here I have taken one question related to this construction of binary search tree from the given data. This question was asked in GTU Winter 2022 exam. So here we will remember this property that the value of every node is greater than every value in the left subtree of n and is less than every value in the right subtree of n. We will construct a binary tree which will satisfy that property. So first thing is we will start with first value in the data, and that we will consider as root of our tree. So I am writing 16 here. Now second value is 24 and it is greater than 16. So 24 must be to the right side of 16. So here I am writing 24. Next value is 7. So we will compare 7 with 16. 7 is less than 16. So if it is less than 16, we will consider it to the left side of 16. So here I am writing 16. Not 16, 7. 7 is to the left of 16 because 7 is less than 16. 24 is to the right of 16 because 24 is greater than 16. Now next value is 5. 5, first we compare 5 with 16. So 5 is to the left of 16. So we will go in this direction. To the left of 16 we have 7. Now we will compare 5 with 7. So 5 is less than 7. Therefore it is to the left of 7. So here we will write 5. Because 5 is less than 16, it is to the left of 16. To the left of 16, this value is 7. So we compare 5 and 7, and because 5 is less than 7, 5 is to the left of 7. Next value is 8, and 8 is again less than 16. So it is to the left of 16. Now we go in this direction. So we have 7. Now we compare 8 with 7. 7 is less than 8. So we will consider 8 to the right of 7. Next value is 20. 20 is greater than 16. So we will go in this direction. So here we are going to the right of 16. First value is 24 and 24 is greater than 20 or 20 is less than 24. So it is to the left of 24. Then next value is 40. So we compare 40 with 16. 40 is greater than 16. So we go in this direction. Then we compare 24 and 40. 40 is greater than 24. Therefore 40 is to the right of 24. And next last value is 3. So 3 is less than 16. Therefore it is to the left side of 16. So here we have 7. So 7 is greater than 3 or 3 is less than 7. So we have to go to the left of 7. So I am going in this direction. I am not going in this direction because 3 is less than 7. Therefore 3 is to the left of 7. And then we compare 3 with 5. 3 is less than 5. Therefore 3 must be left side of 5. So this is the binary search tree for the given data. Okay, we can repeat again because changing colors has disturbed us. So we can again consider this problem. I am changing one color only now. First we are starting with 16. So 16 is the root of binary search tree. Then we compare next value with 16. We check whether the value next value is less than or greater than the previous value. If it is less than previous value, we will go in the left subtree, and if it is greater than the previous value, we will go towards the right subtree or to the right side of that value. Here 24 is greater than 16, so I am going in this direction to the right of 16. Next value is 7. We compare 7 with 16. 16 is greater than 7 or 7 is less than 16, so it is to the left side of 16. Then next value is 5. We compare 5 with 16 first. So 5 is less than 16, therefore it is to the left side of 16. So we go in this direction. Here first value is 7. So we compare 5 with 7, and 5 is less than 7, therefore we put 5 to the left of 7. Then we have 8 here. So again we start by comparing 8 with 16. 8 is less than 16, therefore we should go towards the left side of 16. So here we have 7. Now we compare 7 and 8. So 8 is greater than 7, therefore 8 is to the right of 7. So here I put 8. Then I come to 20. Again I compare 20 with 16. 20 is greater than 16, therefore it is to the right of 16. To the right of 16, first value is 24. So we compare 20 with 24, and because 20 is less than 24, we put 20 to the left of 24. Next value is 40. So again we start by comparing with root, that is 16. 40 is greater than 16, so we go towards right side of 16, and first value is 24 that we compare with 40, and because 40 is greater than 24, 40 must be to the right side of 24. Then we have 3. 3 is less than 16, so we go towards left side of 16. Here we have 7. So again 3 is less than 7, so I should go to the left side of 7. I will not go in this direction because 3 is less than 7, so I will go in this direction, and next value is 5, which is greater than 3, or 3 is less than 5, so here I will put 3. And we can count the number of nodes: 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So this is the required binary search tree. So in this way you can easily construct a binary search tree from the given data. What you have to take care is that suppose I have any node denoted by capital N, then if value of its children is less than n, then we will put it to the left side of n, and if value of child is greater than n, then it goes to the right side of that node, particular node n. Here we compare that towards the left side of 16 all the values are less than 16, and towards the right side of 16 all the values are greater than 16. So in this way they can ask you to write down the binary search tree or to construct the binary search tree from the given data, and you can easily construct in this way. All you have to remember is this definition, that a binary tree is a binary search tree if every node n has the value greater than every value in the left side of n, and value of node is less than every value in the right subtree of n. So this is all about this session. I hope you like it. Thanks for watching.